So gases don't really interact with each other at all. They're separated by these huge distances, but liquids and solid have particles that are very close to each other. I don't think it's this book, but one book I used said touchingly close, and I like that expression. So liquids and solids both have molecules that are touchingly close as opposed to the gases. But what's the difference between liquids and solids?
They're not fixed.
In liquids, the molecules are not fixed relative to each other. They can slide around, right? So I sometimes use the student analogy for solid liquids and gases, but there's also a cow analogy, which I think is especially appropriate out here in Tulare, right? We've got cows just across the parking lot. So the gas state for cows would be out on the open range. The cows just spread out and they're off, lots of space. The liquid state of cows would be the feedlot. You've got all these cows crammed in a small area, right? But they can move around. Bessie and Daisy do not always have to be right next to each other. The solid state of cows is when you've got them in the barn in their stalls. Now Bessie and Daisy are next to each other and they can't get away. They are not absolutely still. They're switching their tails and chewing their cud and shifting around in the stall, right? So in liquids, even though the atoms are very close, they're still free to move around. But in a solid, those atoms or molecules are fixed in position. The intermolecular forces are holding them in a fixed position. They're vibrating. Thermal energy allows them to vibrate, but they can't actually move relative to each other. If you increase the temperature, though, that vibration increases, and eventually you'll get to the point where that vibration is enough to overcome the forces. You might think of a cow just getting really agitated for some reason. Cows don't strike me as real agitated creatures, but we can imagine, right? So the cow just like goes berserk and is, jouncing around in its stall and kicking and stuff. Could it possibly kick out the stall? It could, if it had enough force, enough motion. So that's what happens when a solid melts. All the particles get more and more agitated until they break down those barriers and they move relative to each other. Here's pictures. So here's the gas. Lots of space between the particles. In the liquid, they are close together, but they're just jostling around and swimming around. And in a solid, everybody's lined up and they're all sitting there and they're wiggling, but they can't move relative to each other.
Whenever the solids are sitting there vibrating
Mhm.
in the same fixed spot, do they vibrate in a pattern in a way, or do they just kind of do whatever they do?
That's a good question. When those solid molecules are vibrating, do they vibrate in a pattern or what? Well, they actually vibrate randomly. So they vibrate randomly, and so some are moving left and right, and some are up and down, and it's just all random. Have you seen the phenomenon where an opera singer will hit a high note and a wine glass shatters? That's what happens when you get sound waves causing the particles to vibrate together. Sound waves cause the molecules to vibrate, and if they're all vibrating together and you hit just the right frequency for all of them to vibrate together, then that will shatter the glass. It'll have enough energy to break those bonds that's holding it together. Brief review of properties of these different states of matter. Gases have low densities, indefinite shape, indefinite volume, weak intermolecular forces. Basically, the attractions between gas particles are so weak that they can't hold them together at all. Liquids, higher densities compared to gases, still the indefinite shape, but now they have a definite volume. You can change the size of the container, the volume of the gas won't change, the liquid won't change. So liquids have moderate intermolecular forces. They're holding the particles within this volume, but still allowing them to slide around relative to each other.
When you say not easily compressed, does that mean that liquids are compressible?
We like to think in terms of absolutes, and yet we know in real life that most things are a continuum, right? You can say, oh, well, this person's poor and that person's rich. But in between, there's not a sharp line that divides those, right? So practically speaking, liquids are not compressible, especially compared to gases. Are they completely not compressible? Well, I wouldn't really say that. But practically speaking, they're not compressible. Which is a good thing, or your brakes on your car wouldn't work. Solids have high densities in comparison to gases. Their densities, though, are comparable to those of liquids. They have definite shape. They retain their shape regardless of the container that they're in. They have definite volume. Solids are not easily compressed either. We can have crystalline solids or amorphous solids. Morph refers to shape, and the prefix a means without. So without shape, meaning that there's no pattern to how the molecules are arranged. Crystalline means that there's a certain pattern. They're all lined up in rows. And then we've got strong intermolecular forces. Those strong intermolecular forces are what are holding the particles in these fixed positions. Oh, we're just going on and on and on about this. We just don't have time for that. We said that. Okay.